Today, let's go over weekly contest 412. The first question is final array state after k multiplication operations 1. We're given an integer array nums, an integer k, and an integer multiplier. We want to perform k operations on nums, and in each operation, we want to first find the minimum. If there's multiple, pick the first one, and then replace the minimum with its value times multiplier. And we want to return the final state of nums after performing all k operations. Because the constraints are small, we can brute force this. We first make a min heap of pairs of nums and its index. The reason we store the index is because the heap will reorder the elements. However, our final nums must have the same order as it started with. We simulate k operations where we pop the minimum and then add the new value back to the heap. Now we can simply rewire the numbers to their original indices. The second question is count almost equal pairs 1. We are given an array nums consisting of positive integers, and we call two integers almost equal if they can become equal after performing the operation at most once, where we can choose either of the two integers and swap any two digits within that integer. And we want to return the numbers of pairs of indices such that nums of I and nums of j are almost equal. So we can simply solve this using brute force. So first, we can consider all pairs I, j. If they are already equal, then we don't need to swap. Otherwise, we try to swap each one to the other one, and if they're almost equal, we increment our final count res. And so in our almost equal swap function, we just try swapping every pair of digits in nums and see if it equals target. If it works, then these are almost equal. Since the numbers have at most 7 digits and there are only 100 numbers in the original array, this is very fast, around O of n squared d squared time. The third question is final array state after k multiplication operations 2. So this is the same as problem 1, but k can be huge now. Note that this is not my code. For the next two problems, they're from Aweiss. The idea is to simulate like in problem 1 until the cycle repeats. When the cycle repeats, we will process the elements in order. And so if we have p remaining operations, we know exactly which elements to process depending on the div mod of p. Okay, but how do we know when the cycle repeats and that the elements will be processed in orders afterwards? If we think about the log of each value, multiplication by m turns into addition by log m. This means that in terms of logarithms, we basically only increment each number by a multiple of log m. Now imagine we have some threshold, for instance the maximum number in the array. When we go above this threshold by adding multiples of log m, we cannot exceed by more than log m, since we would have stopped the previous time. So basically, after we simulate the operations until every element is at least the threshold, we now know that all elements in terms of their log values are within log m of each other. This means when we operate on the minimum element, i.e. incremented by log m, it now gets pushed back to the very right end. Now if we have p operations remaining, and p equals q times n plus r, where n is the length of the array, then all elements are now processed q times, and the first r are processed an extra time. Remember, because they are now processed in order left to right. Now that we know how many times each element is processed, we store that in a count array, and then just multiply the number by m to the power of count I. If you're wondering why we can think about log values instead of their actual values, it's because log x is a monotonic function, so it preserves the order of the original values. Because if x is less than y, then log x is less than log y for all xy. Meaning if we just want to compare the relative magnitudes of what happens when we operate on the minimum, then it's okay to compare the log values as well. And because it's easier to reason about addition than multiplication, and logarithms convert multiplication to addition, it makes sense to try to reason about the log values instead. The last question is count almost equal pairs 2. This is the same as the second question, but now we can use at most 2 swaps in our almost equal definition. We need to make this faster since the constraints are larger. Let's consider a function that generates all the possible almost equal numbers from a given number. We can brute force this by considering all pairs of combinations of digits to swap with replacement because we can still do 0 or 1 swaps, and another pair of digits to swap. Now just add the new number after we simulate the swapping. Now we can't just iterate over all pairs of indices in nums anymore because n is up to 5,000. We realize that when comparing any two almost equal numbers, if they have the same number of digits, we can swap either one to the other. The order doesn't matter. If one has more digits, then that one must be the one that's swapped to have less digits by swapping a 0 to the front. This means if we sort by largest numbers first, so most digits first, and using a two-sum approach where we increment the count of almost equal numbers we can swap into from x, we can correctly compute the total number of almost equal pairs. The time complexity of this is O of n times d to the 4 plus n log n. So that's it for LeetCode Weekly Contest 412. Thanks for watching and subscribe for more.